Hi, welcome to Unit 6, Day 8, Part 2, Calculating Empirical Formulas. So we've already learned in Part 1 that there are two types of chemical formulas, the molecular formula, which is the chemical formula for the actual molecule, and the empirical formula, which is sort of a simplified molecular formula. And in the empirical formula, it shows the smallest whole number ratio of atoms in the molecule. And we have an example here with benzene where the actual formula is C6H6, but the empirical formula, or the simplified version, is CH. We also learned why it's important for scientists to be able to determine the empirical formula. And one reason why it's important is because when a scientist synthesizes or makes something in a lab, they need to be able to determine if the product that they made is actually what they expect it to be. Now, sometimes you can tell because it's a well-known reaction, there really isn't much to do. But in many cases, you actually have to analyze your product to make sure that it's pure and it's actually what you want it to be. And one technique for that is elemental analysis. So in elemental analysis, the data that you get provides you with the mass percent of the elements in the compound. And then you can take this mass percent and use it to get your empirical formula. And if the empirical formula that you get from this data matches the empirical formula of the product you were trying to make, then that's evidence that your product that you made is what you wanted to make. So what we're going to do is we're going to learn how to calculate the empirical formula from this sort of elemental analysis data, this mass percent. And then later on, we're going to determine the molecular formula from the empirical formula and molar mass. Now, before we go any further, you may be wondering, how is this even relevant to what we've covered so far? Now, in this unit, we've been learning about moles and how to convert to and from moles. And a key step in determining the empirical formula from the mass percent is converting from mass to mole. So what we're learning here is relevant in the sense that we're going to be using some of the same strategies and tools that we've learned in this unit. And it's also a real world application. So now let's get into determining the empirical formula from the mass percent. Now, when I was in high school, my chemistry teacher taught me this poem that I actually still remember. This is, decades later. That's been super helpful for memorizing the steps to go from the mass percent to the empirical formula. The poem goes percent to mass, mass to mole, divide by small, times till whole. And this poem will hopefully help you in memorizing these steps. So let's take a look at an example problem. An unknown compound was analyzed by elemental analysis, and the mass percent were determined to be 30.45% nitrogen and 69.55% oxygen. Which of the following could be the unknown compound? So what we're trying to do here is, from this elemental analysis data, the percent of nitrogen and oxygen, is determine what the compound can be, because once we get the empirical formula, we can match it to one of these choices here. So how will we set up this problem? Well, I like to set up this problem in a table. And I write in the first column of my table the elements, so nitrogen and oxygen, and next to them I would write their percentages. Okay, so after we have the percentage of nitrogen and oxygen, the next thing is to go from percent to mass, like the poem says. Now, in going from percent to mass, all we're doing is we're assuming we have a 100-gram sample. So if you have a 100-gram sample, the percent and the mass will be the same. So the mass will then be, for each element will be the same as the percent. So basically change the percent symbol to G for grams. Now the next step, percent to mass, now it's mass to moles. Now we know how to convert from mass to moles, right? So we're going to use our dimensional analysis. We take our given, which is the mass, over 1 times 1 mole over the molar mass, or I should say the average atomic mass that we get from the periodic table. And so here I've calculated the moles of nitrogen to be 2.17 and the moles of oxygen to be 4.35. All right, next up, we did percent to mass, mass to mole. Now let's divide by small. So let's talk about that. What we're going to do is we're going to find from our moles the smallest mole value. So between the two of them, 2.17 is the smallest number. And now what I'm going to do in the next step is divide each of the moles that I got in the previous step by that smallest value, right? So I got the moles of nitrogen I have is 2.17. So I'm going to divide the 2.17 by 2.17 to get a 1. And then for oxygen, I got 4.35 moles. So I'm going to divide the 4.35 moles of oxygen by 2.17, and I get approximately about a 2. And at this stage, what I like to do is I like to use no more than 1 decimal here, if I can. Now, in this step, the last step, which is times to whole, what you're going to do there is if you get a decimal number, and I mean like 1.5 or 1.25 or 1.3, like a real clear decimal number, not something that you can easily round to a whole number, then what you need to do is you need to multiply it by the same number and multiply all of the answers you got here by the same number until you get whole numbers. Now in this case, they're already whole numbers, so I can stop. I don't need to do this step. Okay, so what does this information give me? This step here, when I divided by the small, that actually gave me the ratios, the molar ratios of each element. So it's telling me I have 1 nitrogen to 2 oxygens. And that is my empirical formula. Now, again, if these were decimals, I'd have to turn them into whole numbers, sort of like what we did when we were balancing equations for the combustion reactions. And we had to multiply the coefficients to get them to be whole numbers. But here in this example, they're already whole numbers, so I don't need to do that. And I have my ratio of nitrogen to oxygen. It's 1 to 2. So the empirical formula is NO2. Once I have my empirical formula, I can go back and figure out, well, which one does that match? Okay, NO2, and the answer would be choice B. Because as you can see here, that choice B, N2O4, is the only molecule that empirical formula is NO2. Notice that the ratio of nitrogen and oxygens are the same, 1 to 2, 1 to 2. All right, let's try another example. So in this case, the elemental analysis provides us with 48.6% carbon, 8.16% or hydrogen, which I actually changed to 8.20, and 43.2% oxygen by mass. And we're looking for the empirical formula of the unknown. So let's go ahead and do this same process, percent to mass, mass to mole, divide by small times the whole. So the first step, percent to mass, all we do is we take the percentages for each element and turn them into grams. Second step, we are going to use dimensional analysis to convert from our mass to moles. So our work for that looks like this. Remember these numbers here, like the 12, the 1, and the 16, that comes from the periodic table. Now that we've gotten the moles of carbon, hydrogen, and oxygen, we now need to get the molar ratios. And that's what this next step does, dividing by the small. So we have to pick the smallest mole, in which case it's the moles of oxygen, and we're going to divide all of the other moles, including oxygen, by that number. Okay, and this is what we get here when we do that. So the 4.05 divided by the 2.7, the 8.12 divided by the 2.7, and the 2.7 divided by the 2.7 gives us our molar ratios. So what this is telling us that the ratios, it's 1.5 carbon to 3 hydrogens to 1 oxygen. Now, the last step here is if we get a decimal, we need to multiply it to get them to be whole numbers. And that's because the ratios have to be in whole numbers. Okay, so in this case, the only decimal I see here is the 1.5. Now, if I want to make that a whole number, I can just multiply that by 2. The smallest number I can multiply 1.5 by to get it to be a whole number is 2. And whatever I multiply the carbon by, I need to multiply all the other elements by that same number as well. So that gives me 3 for carbon, 6 for hydrogen, and 2 for oxygen. And therefore, the empirical formula is C3H6O2. Okay, so the process here is going from the percents, mass percents, to the mole ratios. So when we divide by small and then multiply to the whole, that's when we get our mole ratios. And then from there, we can get our empirical formula. All right, I want you guys to try it with this CFU. So you can read the problem, pause the video now, and on a separate sheet of paper, try and solve it. When you press play again, the answer will be revealed. All right, so here is the work for this problem. And we get the empirical formula to be C3H4O3. Now, the last thing we're going to talk about is the molecular formula. So remember something like if you look at benzene and acetylene, they both have the same empirical formula, CH. And because many molecules can have the same empirical formula, it's actually better to use the molecular formula to identify a molecule. If you're trying to identify if your product is your product, you want the molecular formula. But there's actually a way to get the molecular formula from the empirical formula, and it's actually quite simple. So let's talk about how do we do something like that. We're going to tackle a problem like this, but before we tackle a problem like this of getting our molecular formula from the empirical formula, I just want to remind you of how we can get the least common factor from the molecular formula and empirical formula. So remember, the least common factor is the number that you would divide the molecular formulas by, the subscripts in the molecular formula, to get the empirical formula. It's the number that you would use to simplify it. So how would we find the least common factor from the molecular formula and empirical formula? What you're going to do is if you take the molar mass of the molecular formula and the molar mass of the empirical formula and divide them, you get the least common factor. So that's a process that we're going to be doing here. So let's go ahead and tackle it in this problem. If the molar mass of your unknown from example problem 1 is actually 148 grams per mole, what is its chemical formula? So in problem 1, we determined the empirical formula to be C3H6O2. Now what we're going to do is we're going to use this information and the molar mass of the molecular formula, so the actual molecule, to get the molecular formula. So the first step is to find the least common factor by dividing the molar mass of the molecular formula by the molar mass of the empirical formula. So the molar mass of the molecular formula is given to me, but I had to calculate the molar mass of the empirical formula by using the periodic table. And here's my work here. So now what I'm going to do is take the 148 and divide it by the 74.06. And that gives me a least common factor of 2. Now the last step is to multiply the subscripts in the empirical formula by the least common factor to get the molecular formula of the molecule. So that sounds like a bunch of words, but simply what I'm going to do is I'm going to take this 2 that I got here and multiply all the subscripts in the empirical formula by that 2 to get the molecular formula. So this is what my work looks like. I just distribute that 2 to all of those subscripts. So 2 times 3 will give me 6 carbons, 2 times 6 will give me 12 hydrogens, and 2 times 2 will give me 4 oxygens. And that's my molecular formula now. All right, why don't you go ahead and try it with your with this CFU. So in this case, you're using the information from CFU 1. And if it's helpful for you, I'm just going to write the empirical formula from CFU 1. So you can go ahead and pause the video now, and when you press play again, the answer will be revealed. Okay, so we're going to find the molar mass of our empirical formula. I divide the molar mass of the molecular formula by the empirical formula, and I get a least common factor of 2 here as well. All right, and then I'm going to distribute that to the empirical formula, and now I get a molecular formula of C6H8O6. So the overall process in going from mass percent to the molecular formula is you get your mass percents, you do the process to go percent to mass, mass to mole, divide by small, times to whole, until you get your mole ratios and your empirical formula. From your empirical formula, you can use the molar masses to get the molecular formula. And then from there, you can use that to identify your unknown. All right, that is it for this video. And so now you have a small, quick exit ticket after this. I hope you found this video helpful. Have a quality day.